Hey everyone, welcome back. Well, this week I've been taking a look at a book that's in my collection, which is this one here, the Z80 Microcomputer Handbook by William Barden Jr. And I thought it would be interesting to share some of the information in this book with you, for those of you who might be interested in the more technical aspects of how the Z80 microprocessor actually works. And I think this stuff is really cool to really be able to understand the really low-level stuff about how the computer works, and particularly the microprocessor. So in today's video, that's what we're going to be looking at. I'm going to share with you a look at the actual signals and pins on the Z80 microprocessor chip itself that's inside both the Sinclair Spectrum computers and essentially the ZX Spectrum Next computer as well, and of course the Timex Sinclair computers. And we're going to take a look at some of the signals and just discuss a couple of the cool features that I found. So if that sounds interesting to you, stick around and we're going to get right into it right now. Alright, so as I mentioned in the intro, we're going to be taking a look at the signals on the Z80 microprocessor chip, which I found some descriptions of in this book. And I'm going to be sharing that with you, some of the more interesting points that I found that you might find interesting as well. I don't know, hopefully you will. And also we're going to be taking a look at the timing for the Z80 microprocessor chip as well. So we're going to be taking a look at a timing diagram and seeing exactly how the microprocessor does the timing in relation to the different pins and the different signals on those pins, to see how the microprocessor can actually operate and do its job of carrying out the execution of the instructions in our Z80 machine code programs. So I'll just bring over a copy of this book here that I found. It's actually available for download online. There's a free PDF you can find online, and I'll put a link to that in the video description as well. And I will also upload a copy of this book in PDF version to the SpriteWorks Facebook group for the Patreon subscribers who have access to the Facebook group. They can go ahead and download that now if they want to take a look at it. So here is the book that I found. It's the Z80 Microcomputer Handbook by William Barden Jr. And there are some interesting aspects of the Z80 microprocessor that I wanted to share with you. So let's take a look. So if you're not already familiar with the Z80 microprocessor chip and the internal architecture of an 8-bit microcomputer, you might want to go back and take a look at the video that I made on that subject if you like. And it essentially describes the different aspects and different parts of an 8-bit microcomputer. And here on my screen you can see there's a diagram that shows some of the main parts of the Z80 microprocessor shown in block form. So if we take a look up here, you can see this top rectangle here is the Z80 microprocessor chip, and it contains some different functions and different functional blocks inside of it. For example, here's the ALU, which is the arithmetic and logic unit, which does the arithmetic computations. There's a data bus control, and there's a CPU register section, which we took a look at the registers in several different of my videos, but they're also listed down here. You see we have the A and F register, B, C, D, E, H, L. All these registers should hopefully look familiar to you by now. And it also shows the other different blocks inside the Z80 microprocessor. There's an instruction register, there's a CPU control signals section listed here, and there's an address bus control section. So basically the Z80 microprocessor, as I'm sure you know, consists of address bus, a data bus, and some control lines. So let's take a look at those in a bit more detail now and look at some interesting features about them. So if I scroll down now, I'm going to go to the part where it shows the actual pinout for the chip, which is right here. So the first thing we should take note of is that this diagram shows the pins organized according to their function rather than their actual layout and position on the physical chip itself. So here at the top here you can see the address lines, which are the pins that contain values to indicate a particular memory address that the chip might be interested in. And you can see there's one arrowhead on the left side of these lines, which means that these are output signals. So what does an output signal mean? It means that this Z80 microprocessor chip is what controls the value that's going to be on those lines. They're not controlled by the outside circuitry, they're controlled by whatever this Z80 microprocessor wants to put on those lines. So we can see all of these address lines are output lines. So the Z80 microprocessor chip decides what values will appear on those address lines. And then down below those address lines here on this diagram, you can see there's a section with the data bus, and these are the data pins, which represent the value of the actual data that's stored in the memory locations, as I'm sure you know. And here you can see these arrows have double heads on them, meaning these are both input and output lines. So the data that appears on these data lines, or the values of the data that appears on these data lines, can be controlled either by the Z80 microprocessor chip, in which case they would be outputs, or they can also be controlled by external devices, particularly memory chips. So they would also determine what values appear on these data lines. So these data lines, since they have two arrowheads on them, are both input and output lines. They are bidirectional signals. All right, so let's take a look at some of these other signals here and see what they do. So here up at pin number 25 here, we have a signal which is an input because the arrow is pointing in towards the chip, and it's called bus RQ, which stands for bus request, and you can see it has a line over top of it. So these signals that are shown with a line over top of it means they are active low. So as you probably remember from either your own knowledge or from my other videos, these signals are using what's called digital electronics, which means they can have one of two possible values, either 0 volts or plus 5 volts, which corresponds to binary digits of either 0 or 1. And so all of these signal lines here use this digital electronic circuitry, which means they would at any time have either 0 volts or plus 5 volts on these lines. And the signals here that are shown with a line on top of them means they are active low, which means that they do what they're supposed to do when the signal is low. So when there's 0 volts on that particular line, that means that particular line or that signal is active. So in this case, pin number 25 is connected to a signal that's called bus RQ, which is also known as bus request. And what does this do? Well, since it's an input, that means it's controlled by an external device, some kind of I/O device or input-output device. And essentially what this does is it tells the Z80 microprocessor when an external device wants to control the buses, which is why it's called bus request. So let's say there's an external device connected to the computer and it wants to use the buses for whatever reason. For example, it might want to access the memory chips directly using a feature known as direct memory access, or DMA. So if an external device wants to directly access the memory chips, for example, and it doesn't necessarily want the Z80 microprocessor to be involved in that process, then it would send a bus request signal to this pin right here, and it would tell the microprocessor, hey, I want to use the buses and some of the other control lines. So once you're done executing the current instruction, then let go of those bus lines because I want to use them, and the Z80 microprocessor will respond to that. And that takes place down here on the next pin, 23 right here, which we can see is labeled bus ACK, which stands for bus acknowledged. So when the bus request line goes low, that means an external device wants to access the buses. And by the buses, of course, I mean these address bus lines over here and the data bus lines and some other control lines. So when an external device wants to, for example, access these buses, it would send this bus request line low by putting 0 volts on it. And then you can see this bus acknowledge line is an output line. And what happens there is once the Z80 microprocessor is finished executing its current instruction, because of course that's the purpose of the Z80 microprocessor, is to execute the instructions in our machine code program. So once it's finished executing whatever current instruction it's working on, it will recognize this bus request signal from the external input-output device, and it will release the buses, essentially. It will let go of them. And we're going to take a look at this in a bit more detail later when we take a look at a timing diagram, which is pretty cool. So essentially the Z80 microprocessor will say, okay, I know you want to control the buses. I'm going to take my hands off of them. They're all yours. You know, don't hurt me. Do whatever you want to do. Take control of the buses. I'm done with them. And just let me know when you're finished. So at that point, when the bus acknowledge signal goes low, that is the Z80 microprocessor telling the external device, hey, I'm done with the buses. You can use them. Let me know when you're done. Now let's take a look at these lines down here, which you can see they are all output lines. These pins 19, 20, 22, and 28, and they're labeled MREQ, which stands for memory request, and then read, write, and refresh. So these three top lines here, memory request, read, and write, they're used for performing memory access functions. So when the chip, this Z80 microprocessor, wants to access the memory, for example, it would use these lines to tell the memory chips that it wants to access them, and it would also indicate whether it wants to do a read operation or a write operation. Based on which of these two lines, read or write, it puts low, meaning which of these two lines it applies 0 volts to as an output. And then here there's another signal called RFSH, which stands for refresh. So you may or may not be familiar with the different types of memory, and we discussed in the architecture video that there are two types of memory called RAM and ROM, which stand for random access memory and read-only memory. Well, there are also actually, well, at least two types of RAM memory. There's what's known as dynamic memory and static memory. So static memory, it retains its value of whatever data is in the memory as long as it has power, but the dynamic style of memory needs to be constantly refreshed, and it gets refreshed by applying signals to these address lines and the data lines that are connected to those memory chips. Otherwise, they kind of lose their charge and they forget what data is stored in those memory locations. So in order to keep that data refreshed, that happens by a signal here called refresh, and it is used to control that refresh process. So now let's take a look at the other pins and see what we can find. So here on pin 20 is an output that is labeled IORQ, which stands for input output request. So when the Z80 chip wants to do some sort of input output function, then it activates this line. Pretty straightforward. And here we have a signal called M1, and we're going to be taking a look at this more when we take a look at the timing diagram for the Z80 microprocessor chip. And it is used to control the timing of the instruction that is being carried out. And again, like I said, we're going to be taking a look at that in the timing diagram. So now let's take a look at these signals here. On pin 26 here, we have a signal called reset, which again is active low. Like all of these signals are actually active low, which means they get activated by pulling them low or pulling them to ground or pulling them to 0 volts. It all means the same thing. So this reset signal, as you can see, it's an input. It does exactly what you would expect. It resets the chip. And if we want to, we can take a look at the text in this book to see specifically what happens when this reset line gets pulled low. Alright, so if I scroll down here to this section, where here it says, when reset is brought low, the following actions occur. And so here it lists all the different things that happen when that reset line goes low. The first thing that happens is the interrupt enable flip-flop is disabled, preventing system interrupts except for NMI, and we'll discuss that in a moment. So we don't really need to worry about what these steps mean, but it's kind of interesting to see that just setting that reset line to low performs all these different functions. So let me go back up to the pinout of the chip here again, and that is the reset line. So what do we have next? Here we have pin number 24, which we can see as an input, and it's connected to a signal called wait. So what does the wait signal do? Well, the wait signal, since it's an input, that means it's controlled by some external device or some external circuitry, and this would be some sort of slow device. So if there's an external device connected to this microprocessor chip and it needs time to finish doing whatever it's doing, it might tell the microprocessor, hang on, I'm not finished doing what I'm doing yet, so just don't do anything until I'm finished what I'm doing, and then you can continue on with what you're doing. So when this wait signal goes low, essentially the Z80 microprocessor chip does nothing. It just hangs around waiting. And we can take a look at the text and see how it describes that right here. It says the wait signal is a signal associated with slow memories or I/O devices. As long as the wait signal is low, which means it's active, the CPU will mark time doing nothing, while the external memory or I/O device responds to a previous memory or I/O device request. So the wait signal enables slow memories, or rarely slow I/O devices, to be interfaced to the Z80 without buffering. So essentially, the wait signal will tell the CPU to not do anything, just hang out and wait for the external device to finish whatever it's doing. And I'll go back up to the pinout here and we'll see what's next. Alright, the next pin on pin number 18 here is a signal called halt, which is an output, And that gets activated actually by software. When we program the microprocessor to execute a halt instruction in Z80 assembly language, it sends this output low. So this is controlled actually by us, by the programmers, to determine when this output goes active or when this halt line gets set to low. And if we take a look at the text here, it says the halt signal is an active low output signal that goes low during the time that a halt instruction is being executed by the microprocessor as part of our program. And it says a halt instruction in a program is typically used for one of two conditions. Either the program has performed all of its functions and has terminated, or a halt has been reached and the program is waiting for an interrupt to occur. When the CPU is in a halt state, it performs no operation instructions, NOP, to ensure proper memory refresh activity. So this sentence is kind of interesting to take note of. It says when the CPU is in a halt state, then it performs no operations instructions. And that doesn't mean that it performs no instructions. That means it is performing an instruction, but it's performing one specific instruction, this NOP instruction, which stands for no operation. So the CPU will continually execute this NOP instruction or no operation instruction, essentially until an interrupt occurs, which we'll take a look at in a moment as well. Next we have pins 16 and 17, which are interrupt inputs. And we discussed interrupts briefly in a previous video. And you can see these two lines that are labeled int and NMI, which you may already know stand for interrupt and non-maskable interrupt. And there's something actually interesting about the non-maskable interrupt. As you probably know, an interrupt would be generated by a device, maybe let's say a keyboard or something, that can interrupt the processor from whatever it happens to be executing as part of our program. And regular interrupt signals can be enabled or disabled because they're what's known as maskable. However, this NMI signal, which stands for non-maskable interrupt, is just that, it's non-maskable, which means it can't be disabled. However, there are two interesting aspects to this non-maskable interrupt that you might not be aware of, and let's just go take a look at them now. Alright, so here's the section on interrupt related signals. Well, we know that digital circuits can be at one of two states, either 0 volts or plus 5 volts. So normally you might think it's logical to assume that all the analysis of these lines is done based on their levels. So you might expect the operation of the computer to be determined by the different levels on all of these digital signal lines. However, you can see here it says the NMI signal is a negative edge triggered input, which means it doesn't get triggered based on its level, either high or low, but rather it gets triggered as it's transitioning from high to low. So it's kind of maybe breaking the rules of digital circuitry in that respect, if you think about it that way. It's not actually interested in what level it's at, but rather the CPU looks at when this signal line transitions from high to low. So that's kind of interesting. Now let's see what else we can learn about the NMI input. It says when this signal is momentarily brought low, the CPU will recognize this interrupt at the end of the current instruction. So it's not going to instantly interrupt the microprocessor no matter what it's doing, where it is in its instruction cycle, because as we're going to be seeing in a moment, the assembly language or machine code instructions actually get carried out in a series of different cycles. And so the actual instruction, although it might be made up of several electrical cycles, this NMI signal will have to wait until the microprocessor is finished executing whatever current instruction it happens to be working on. And when it does that, these two things will happen. It says when the CPU recognizes the NMI interrupt, the following actions occur. And at this point in the video, or probably much earlier in the video, you might be wondering, does this information really apply to us as programmers in making games? Do we really need to know what's happening at the level of the chips inside the computer to be able to make our games? Well, obviously no, we don't need to know exactly how all these signals are working. But like I said, I'm just documenting my journey, and this is what I worked on this week, so I find it kind of interesting and I'm going to share it with you. But there are, I think, parts of this information that are actually useful to us as programmers and game developers. And let's take a look at this as an example. So here it says this is what's going to happen when the NMI or non-maskable interrupt signal gets activated. And the first thing that's going to happen is the current contents of the program counter. So we know all about the program counter from our assembly language programming experience. And it says the program counter is saved in the memory stack. And again, we should know what the stack is. And if either of these is confusing to you, you might want to go back and watch some of my previous videos. But obviously the program counter is being saved on the stack because when you press that NMI button, or if that NMI signal gets activated, for example, if I were to open up my computer, if I take my Timex Sinclair 1000 computer and I open it up and I take a paper clip and I short out that NMI line on the Z80 CPU to ground, and I'm not telling anyone to do this, I'm talking about my own computer, so don't blame me if you try this and your computer gets damaged, because I'm certainly not recommending that anyone do this. But literally, if I were to open up my computer and take a paper clip and connect one end of it to this NMI pin on the Z80 CPU and the other end of it to ground, or any point on the board that is at 0 volts on the ground plane, they call it, this is actually what would happen. So the current contents of the program counter would get saved on the memory stack. And then if I scroll down here, step number 2 says the CPU transfers control to memory location 0066 hexadecimal. Now I'm not sure if this address is actually valid in the ZX Spectrum Next or the different Sinclair Spectrum computers, but the interesting thing to note is what happens when the NMI or non-maskable interrupt signal gets activated. And we can see that happen in the ZX Spectrum Next computer. For example, on the side of the computer is a button that's actually labeled NMI, and if you press that button, it's going to bring up a menu on the screen, and the way it does that is by executing a certain specific NMI handling routine that gets activated when that button gets pressed. Now I just want to take a look at this other paragraph here that follows, and if you're at all interested in these electrical signals and how they work, this next part I think is pretty cool, and let's take a look and see what it says. It says an NMI interrupt of this kind cannot be disabled. So that makes sense. It's a non-maskable interrupt, which means it's not maskable, which means it can't be disabled, which is what it says. And it says it will always be recognized by the CPU at the end of the current instruction cycle. So it needs to finish executing whatever instruction it's currently working on, and then it will recognize the NMI input. However, there are some exceptions, as it describes right here. So even though it's non-maskable, it kind of is maskable in certain conditions, as described here. And let's take a look. It says the exceptions to this are that the signal bus request will take precedence over an NMI signal. So remember, we took a look at this exact signal bus request earlier on, which is activated by an external device that wants to take control of the buses. So if there is an external device that wants to use the buses, the address bus and the data bus, and some of the control lines as well, then this bus request signal line will go low, and that will disable the NMI operation. So that's kind of interesting to know that there is a way to actually disable the NMI operation. So for example, if I were to, again, open up my Timex Sinclair computer and I took a paperclip and I shorted this bus request line to ground, and then if I were to short the NMI signal line to ground, that NMI signal would be ignored because I've already got this bus request shorted to ground, which means it's active. Now there's one other interesting thing here that says a continuous wait state will prevent the current instruction from ending and thus prevent the NMI from being recognized. So remember, we took a look at the wait input signal earlier on as well, and the wait signal is activated by some slow external device, maybe a memory chip or something. So if it's busy doing something and it pulls this wait line low, it tells the processor to just wait and don't do anything for a while until I'm finished doing whatever I'm doing. And if that is the case and this wait line is being pulled low, essentially the effect that has is it also causes this NMI signal to be ignored, but it causes it to be ignored in a bit different way. And the reason it gets ignored in this case is because it prevents the CPU from ever finishing carrying out whatever instruction it's currently working on. So if we take a look at that here, it says the wait signal is a signal associated with slow memories that we took a look at earlier, and it causes the CPU to do nothing, which means if the CPU is doing nothing, then it's not going to finish executing whatever instruction it's on. And since the NMI input, the non-maskable interrupt, only gets recognized after the computer finishes working on whatever the current instruction is, then this wait signal is also going to prevent that from happening. All right, let's go back up to my pinout here and see what else we can look at. And these signal lines are going to be kind of illustrated in what I think is kind of an interesting graphical way when we take a look at a timing diagram in a moment. Of course, all this information is probably more of interest to people who are looking to build their own Z80 based microcomputer, but I still think it's interesting, so I'm just going to keep going here and take a look at the rest of these signals. And so here we are down here at the bottom on pin 6. So pin 6 is the clock input. So the clock input, as you probably know, the Z80 microprocessor needs a clock in order to operate because it needs to have some form of timing to know when to do everything, as we're going to be looking at in a moment. So there's actually a circuit that is shown here for the clock, and I'll just scroll down to it here, which is right here. So you can see they've even included a little circuit of how you would connect the components to the clock input, and then this clock input provides the timing to allow the Z80 microprocessor to carry out its functions. And then finally, if we go back up to the pinout again, right here, you can see the last two signal pins here on pin 11 and pin 29 are the power pins. So pin 11 is an input for the plus 5 volts power input, and pin 29 is the ground, or 0 volts. All right, so now let's take a look at a timing diagram and see exactly how some of these signals actually interact with each other and the effect that they have on the Z80 microprocessor. All right, so let's take a look at this diagram here first of all. And here you can see there's something familiar, which is the clock that we just discussed. And here it's labeled as 4 megahertz as an example. So in this case, they're using an example of a 4 megahertz clock signal. And the way that a clock signal works as an input to the Z80 microprocessor chip is it simply cycles between plus 5 volts and 0. And you can see that right here in this cycle here that's labeled T cycle. You can see it goes up to plus 5 volts, comes down to 0 volts, up to plus 5, down to 0, up and down. And that's how a clock works. It just keeps cycling continuously between plus 5 volts and 0 volts. And every complete cycle is called a T cycle or a T state. So that's pretty easy to understand. One clock cycle is called a T cycle. And now there's a couple other cycles that are of interest to us as well when we're talking about machine code and the timing of the Z80 microprocessor chip. And this part of this video would be of interest to people who really want to optimize their code to make it run as quickly as possible, where even though we're already programming in Z80 assembly language, which gets converted to machine code, which executes very quickly, if you really want to optimize your machine code, then you would be interested in knowing how long different instructions take to execute. So we already know what a T cycle is. That's simply one cycle of the clock input. And then here we can see that there's another label called machine cycle. And down at the bottom here, there's a note that says 3 to 6 T cycles typical. So a machine cycle is simply a period of time that is made up of T cycles. And what does a machine cycle actually do? Well, if we take a look down here in the text, in this example it says there are 7 basic machine cycles that can occur during Z80 operation. So the Z80 chip will perform certain tasks as it executes a program. And depending on what type of instruction it's trying to carry out, that will determine what type of machine cycles or machine operations it will need to perform. And here they are listed right here. So there are 7 different types of basic machine cycles. And this isn't basic programming language. Don't get confused by this basic word. It doesn't mean basic programming language. It just means basic, meaning simple. So here are the different types of machine cycles that the Z80 CPU might carry out. The first one is an operation code fetch cycle, or M1 cycle. So all of the instructions at least will have this M1 cycle as part of its tasks. And then there are other various types of tasks that it might do as part of a machine cycle, such as memory data read or write, I/O read or write, bus request, bus acknowledge, which we took a look at a bit earlier, interrupt request and acknowledge, non-maskable interrupt request and acknowledge, which we took a look at earlier as well, and exiting from a halt instruction. So those are the different operations that might get performed as part of a machine cycle, and depending exactly which operation is being carried out, that will determine how many T cycles are needed to make up that particular machine cycle. So then there's one more type of cycle we need to look at, and that's right at the top here. So these machine cycle segments here are now shown at the top here: machine cycle M1, machine cycle M2, and so forth. And these are made up into something known as instruction time. So when we create a Z80 assembly language program, it's made up of instructions that we want the computer to carry out, and that could be any type of instruction. It could be a load instruction, it could be an increment instruction, it could be a return instruction, it could be a shift instruction, it could be a compare instruction. Any type of instruction that we give the computer to carry out, that instruction is going to be made up of machine cycles, and those machine cycles are made up of T cycles. So it's very interesting to be aware of these different cycles, and I guess maybe necessary to be aware of these cycles if we want to really optimize our program, because we can find out how many cycles it takes for each type of instruction to operate. And if we want to really optimize our code and have it run as quickly as possible, if we're aware of how many machine cycles and T cycles go into making up the particular instruction that we want the computer to execute, then we can figure out more efficient ways of performing the tasks in our program. All right, now this book has a few different examples of timing diagrams, and if you're still interested in this type of information, then timing diagrams might be of interest to you as well, particularly if you're interested in building your own microcomputer. Maybe you are. It's actually not that difficult to do from the information that I've seen, and it's actually one of the tasks that I'd like to carry out at some point. And if I ever do, then of course I'm going to make a video on it, but I think that might be a bit beyond me at this point, although I'm going to keep that in the back of my mind, and you never know. So here, let's take a look at a timing cycle for a particular operation that the computer is going to perform. And of course, these operations all depend on what instructions we give the computer as part of our assembly language program. And this one's pretty cool because it illustrates a couple of the things I mentioned earlier and a couple of the things we just took a look at. So if you're not already familiar with timing diagrams, these are graphical representations of the electronic signals on those pins of the CPU chip that we just took a look at. And the first one I want to show you is this top one here, which should be familiar to us now. It has this symbol here, which is the phi symbol, and this is representing the clock input. And as we looked at before, the clock input simply just cycles between 0 volts and plus 5 volts. It goes from low to high to low to high, up and down and up and down. And every complete cycle where it goes from low to high and back again, that is called the T state. As you can see right here, it's labeled last T state here, TX, TX. So all of these individual cycles of this clock input are the T states. And if we take a look at the top here, in this particular example, it says any M cycle. M cycle refers to machine cycle, which we now know that machine cycles are made up of individual T cycles. So in this case, this machine cycle would be made up of 3 T cycles right here. And now we're going to get into the most technical part of this video, probably the most technical part of programming you will ever need to know in programming a Z80 microprocessor based computer. This is as low level as it gets. We're looking at the actual electronic signals now on the chip. So when you talk about low level programming, this is as low level as it gets. So if you can understand this, then the rest of programming in Z80 assembly language should be a breeze. So remember how we discussed before how there's a bus request signal line that gets activated when an external device wants to access the bus. And so it tells the CPU, I want to access the bus lines. So once you're done with your current instruction, then let go of those lines and let me have them. So let's take a look and see how it works. It says at any time, an external device can gain control of the address bus, which is lines A0 to A15, the data bus, which is D0 to D7, and some of the signal lines, which are listed here: memory request, read, write, I/O request, and refresh lines. And the way that the external device gains access to these lines is by enabling the input signal bus request. which we took a look at a bit earlier. And now we're going to take a look at the timing diagram, which explains exactly how this works in terms of the voltages and the signals on those input lines. So again, like I mentioned earlier, this would happen if the external device wants to access the memory directly, for example, doing something known as direct memory access, which is shown right here, otherwise known as DMA. So let's read how this works. It says, when signal bus request is enabled, and let's take a look at that in our timing diagram. So here we have the bus request line, and normally it's high, which is inactive, and when it gets enabled, it goes low. So let's see, where does it go low? So here we have T cycle number 1, and here we have T cycle number 2, remember, and right here, where it says sample, right here we have the line of bus request going from high to low, and this is happening in T cycle number 2. So when this happens, the bus request line is going low. That means the external device wants to take control of the address and data bus, but it has to wait until the CPU frees them up. So let's go ahead and read the rest of the sentence now. So it says, when signal bus request is enabled, when it goes low, like we just took a look at, the CPU detects the signal during the rising edge of the last T cycle of a machine cycle, which should all make sense to us now, right? So where is the last T cycle of a machine cycle? Well, if we take a look here, the T cycles are at the top here, and the machine cycle is at the very top. So we know that a machine cycle is up here. In this case, this machine cycle contains these 3 T cycles, and it says that the CPU is going to detect this when the last T cycle goes up, which is right here. So here you can see the last T cycle, or the T state. Here it's high, and then it transitions to low, and then it's low, and then it transitions to high. So here is the last T cycle of the machine cycle, and that's what it says in our text here. It says, the CPU detects the signal during the rising edge of the last T cycle of a machine cycle. So the last T cycle of the machine cycle is right here, right? So here's the machine cycle, here's the last T cycle, and this is the rising edge right here. So that is where the CPU detects that this bus request line has been activated. So what happens next? It says the T cycle is then completed, and on the next T cycle, which is right here, here's the next one, right? On the next T cycle, the CPU responds to the request by output signal bus acknowledge. So where is output signal bus acknowledge? Well, it's right here, right below it. So this bus acknowledge signal, it starts out high, and then it goes low when the CPU acknowledges that it sees this bus request line going low, and that happens right here. And so let's try and figure out what we would expect to happen based on our previous discussion when this bus acknowledge line goes low. So what does that mean when the bus acknowledge line goes low? Well, that means that an external device has told the processor, told the Z80 CPU, that it wants to take control of the buses. And then the CPU recognizes that by acknowledging that, by activating this bus acknowledge line, but it also has to do something else, right? Remember, it has to free up those bus lines. And how does it free up the bus lines? Well, we can't have 2 different devices trying to control the same lines at the same time, which means we can't have an external device and the CPU both being connected to, let's say, the address bus and the data bus and fighting to control that. So in this case, the CPU has to let go of its control over those lines. And the way it does that is an interesting way right here. As you can see, right here, when this bus acknowledge line goes from high to low, this is the CPU acknowledging that it has given up control of the address and data lines and these other control lines as well. But how does the CPU actually give up control? Well, the way it does it is by physically disconnecting from them. And although digital signal lines normally have just 2 states, because they're digital, you would expect them to have only one of 2 states, either high or low, either plus 5 volts or 0 volts. But there's actually a 3rd state that they can have, which is called high impedance state, which essentially means they're disconnected. And that's exactly what's being shown right here. If you take a look here, here are the address lines A0 to A15. Here are the data lines D0 to D7. And here are some various control lines that are also included in this bus request activity. So if you look over here, as soon as this bus acknowledge line goes low and the CPU gives up control of those lines, what happens to those lines? Well, Here they just have a dotted line. They're not shown as being either high or low, but they just have this dotted line, meaning that the CPU has disconnected from them. So that's pretty cool. And if we take a look down here, there's a note that says that they're actually floating. So they're not being pulled high, they're not being pulled low. As far as the CPU is concerned, it just let go of them. It says, okay, I'm done with them. External device, you take control of them and just let me know when you're done. And how does the external device let the CPU know when it's done managing these lines? Well, that would happen at the end here. You can see right here, as we would expect, this initial bus request line should probably go inactive again when the external device is finished using these lines, which means it would go high. And where does it go high? Well, right here. You can see here it's going from low to high. So right here is where the external device is saying, I'm done using those lines. CPU, you can have them back. And then at some point, the CPU is going to regain control of those lines, which you can see happens right here, where these dotted lines end and those buses return back to a normal digital signal level. It says, this condition will be detected by the CPU on the next rising edge of a T-cycle. And then where's the next rising edge of a T-cycle? Well, it should be right here, right? So here the bus request line gets deactivated, and then on the next T-cycle, which is right here, the CPU deactivates the bus acknowledge line by making it go high right here. And then you can see in the following T-cycle right here, the address lines, the data lines, and these control lines no longer have dashed lines being connected to them, and they go back to regular digital electronic states of either 0 volts or plus 5 volts, being either low or high. And then finally it says the CPU will then continue processing from the point at which it gave control to the bus requester, which means the CPU will just carry on doing what it did before. And there we have a detailed look at some of the signal lines on the Z80 CPU processor chip, as well as a look at an example of a timing diagram that shows how these signals actually relate to each other. Alright, so if you made it to the end of this video and you understood most of the information that we covered, you should be proud, because this is a video that covers the probably most technical information that we will ever need to know in developing video games, except for possibly if we get into looking at things such as refresh rates and screen timings, and looking at using the copper on the ZX Spectrum Next computer. That might be a little technical as well, but I think we're a bit far away from that point yet. So thanks for watching today's video. I hope it was informative and interesting for you. And remember, again, if you're interested in checking out this information again for yourself and reading some more about it, I'm going to be putting a link to actually an earlier version of this book, because I couldn't actually find this exact printing version available online. But I'm pretty sure the information is pretty much the same, and I'll put a link to it in the video description down below. And again, I want to thank you for watching, and hopefully this video has given us an appreciation for exactly how much control we have when using a low-level language such as Z80 assembly language, which is essentially one step above machine code, which is, as we now know, about one step above looking at the actual electronic signals on the circuit board. So thanks for watching, and we'll see you next time.